Right now, inside a human red blood cell, there is this microscopic shapeshifter, and it's voraciously eating human tissue.
Yeah, literally consuming it from the inside.
Right. And it's generating this highly toxic biological waste while it does it. But to destroy it, our absolute best weapon relies on, well, it's a 1,600-year-old recipe.
Which is just wild to think about.
It really is. A recipe that was secretly rediscovered right in the middle of the Vietnam War. So welcome to today's deep dive.
We have a lot to cover today.
We really do. We are unpacking this massive stack of pharmacological history and science because we want you to understand exactly how humanity wages biochemical warfare against, one of our oldest, deadliest adversaries, malaria.
And the mission for you today is to trace the origins of these drugs. We're going to step right onto that microscopic battlefield.
And uncover the, quite frankly, terrifying modern arms race of drug resistance.
It truly is a relentless arms race. I mean, it spans centuries.
Yeah.
But before we even look at the weapons we've designed, we kind of have to establish what the enemy actually is.
Right out of the gate, we need to clear up a major misconception.
Because the way most of us picture this disease, it's just biologically inaccurate.
Exactly. So if you are picturing malaria as like a bacterial infection or a virus, you need to just erase that from your mind entirely.
Yeah, it's neither of those things.
Malaria is actually caused by a eukaryotic protozoan parasite, specifically from the genus Plasmodium.
And while a few species infect humans, the one that causes the most lethal, severe form of the disease is Plasmodium falciparum.
And that distinction, the fact that it is a complex eukaryote, that is the whole reason this battle is so incredibly difficult.
Right. Think about a standard bacterial infection. A bacterium is a prokaryote. Its cellular structure is vastly different from our own human cell.
It has a cell wall, for example.
Exactly. Human cells lack cell walls, so that difference gives us this massive neon-lit target for antibiotics.
We can design a drug that just destroys cell walls, and we know it won't harm the human patient.
But a eukaryotic parasite like Plasmodium, biologically speaking, it's uncomfortably similar to us. Its cellular machinery looks, well, a lot like our cellular machinery.
Which means you can't just throw a broad-spectrum antibiotic at it, right?
You really can't. If you use a compound that poisons a complex eukaryotic function, you run a very high risk of poisoning the human host at the exact same time.
So to kill it, researchers have to hunt for these incredibly narrow, highly specific vulnerabilities.
Yes. We have to find those rare moments where the parasite does something completely alien to human biology and just exploit that tiny window.
But before we get into those molecular windows, we kind of have to look at how we even define an antimalarial drug.
Right, because going through these historical sources, the definition itself was a massive moving target.
It took us centuries to even realize what we were fighting. For a long time, the definition was, well, entirely symptom-based.
And antimalarial was simply defined as a substance that breaks a shivering fever.
Because these drugs existed way before the germ theory of disease was even a thing.
Oh, absolutely. The earliest major origin story in our sources, it takes us back roughly 350 years to Peru.
Right. Indigenous peoples there were utilizing the bark of the cinchona tree to treat severe shivering fevers.
And then in the 1630s, Jesuit missionaries encountered this practice. They brought the bark back to Europe,
where it earned the nickname Jesuit's bark.
Right. And there's this incredibly pervasive legend in the sources about the Countess of Chinchon.
The wife of a Peruvian viceroy, right?
Exactly. She was famously cured by it in 1638, or so the legend goes.
And the story was so widely accepted that Carl Linnaeus, the renowned botanist, he actually named the plant genus Cinchona after her.
Immortalizing the legend and immortalizing a spelling error that remains to this day.
Right, he misspelled her name.
Yeah.
But it wasn't until 1820 that French chemists finally extracted the pure active compound from that bark.
Which we know today as quinine.
Right. And for about a century, quinine was essentially the only pharmacological defense the world had.
It literally dictated the success or failure of massive colonial military campaigns.
But the way science viewed quinine had to shift dramatically once we actually, saw the enemy.
That paradigm shift happened in 1880. A French physician named Charles Louis Alphonse Leveron looked under a microscope and finally identified the Plasmodium parasite.
Swimming right there in a soldier's blood.
Yeah, and the moment that happened, the definition of an antimalarial upgraded. It no longer just meant breaks a fever.
It meant kills the organism in the bloodstream.
Exactly. But the plot thickens even further because over the next several decades, scientists mapped out the parasite's full life cycle.
And they realized the blood was only one part of the story.
Right. The parasite actually moves through different stages. There's a liver stage, a blood stage, and a sexual stage where it prepares to infect the next mosquito.
So the realization that the parasite shapeshifts, that forced pharmacology to fracture into highly specific categories.
A drug that annihilates the parasite in the blood might be completely blind to it when it's hiding in the liver.
I feel like the best way for you, the listener, to picture this life cycle is to imagine the parasite as this highly coordinated home invader.
Oh, I like that analogy.
Right. It's moving through different rooms of your house. So if you take a drug designed specifically for the bloodstream, you've essentially called in a SWAT team to clear the blood room.
The fever stops, the symptoms vanish.
But if the invader has accomplices quietly hiding out in the liver room, that blood-specific drug is useless.
The accomplices will just wait for the drug to leave your system, step back into the bloodroom, and attack you all over again.
That analogy really highlights why modern malariology requires such insane precision.
You can technically cure the acute symptoms by clearing that bloodroom, but if you ignore the other rooms, the patient will inevitably relapse.
Or they'll just pass the parasite right back into the mosquito population.
Exactly.
So let's move forward a bit. With the supply of cinchona bark largely controlled by colonial powers, and then eventually cut off by the Japanese occupation during World War II, the Allies were facing a massive crisis.
Militaries on the ground in tropical theaters were suddenly losing way more soldiers to mosquito bites than to bullets.
Just sheer desperation.
Yeah.
And that forced one of the most urgent shifts in medical history: the hunt for a synthetic replacement.
The pressure of a global war forced investigators to, well, dig through discarded research.
Right. They took a second look at a synthetic compound called chloroquine.
Which had actually been synthesized back in 1934 by a German chemist named Hans Ondersag.
But early, kind of flawed testing suggested it was too toxic for human use, so they just shelved it.
Yeah, but wartime desperation proved that initial assessment wrong.
Chloroquine turned out to be cheap, highly effective, and easily manufacturable. It became the dominant global drug from the late 1940s all the way through the 60s.
But what is absolutely fascinating is how chloroquine actually works.
Yes, it is molecular warfare that perfectly exploits that narrow biological vulnerability we talked about in the beginning.
The mechanism is elegant because it turns the parasite's own biological needs right against it.
So when Plasmodium falciparum invades a human red blood cell, its primary goal is to eat, right?
Voraciously. It consumes the host's hemoglobin, breaking it down into amino acids to fuel its own replication.
But eating human tissue comes with a dangerous consequence for the parasite.
Right, the digestion process leaves behind a byproduct called free heme.
And free heme is incredibly toxic to the parasite.
It's essentially generating lethal biological waste just by having a meal.
So to survive its own toxic waste, the parasite uses this highly specialized acidic digestive vacuole.
Inside this tiny compartment, it polymerizes the toxic free heme, binding it together into safe inert crystals.
Which are called hemozoin, right?
Yeah.
Often referred to as malaria pigment.
Exactly.
I picture it like the parasite bagging up all its toxic and metabolic garbage into these heavy-duty, leak-proof trash bags.
That's a great way to visualize it. As long as the garbage is in the bags, the parasite is totally safe.
So where does chloroquine enter the picture?
Well, chloroquine is chemically a weak base. Because of that property, it naturally gets drawn into the highly acidic environment of the parasite's digestive vacuole.
It concentrates there in massive amounts.
And once inside, the chloroquine molecules bind directly to the toxic heme and physically block that polymerization process.
Wow, so it essentially glues all the garbage bags shut before the parasite can put the waste inside.
Exactly. And the biological consequence of those glued bags is immediate and catastrophic.
The toxic free heme just builds up exponentially.
Yes. And the parasite's membranes are shredded by its own metabolic waste. It poisons itself from the inside out.
And this works so beautifully because human cells do not digest hemoglobin this way. We just don't have that vulnerability.
It's brilliant. But, you know, nature always finds a way to adapt.
Always. By the late 1950s, chloroquine was failing spectacularly. The parasite evolved this single-point mutation in a transporter gene called PSEIT.
And that tiny genetic typo gave the parasite a whole new defense mechanism.
That mutation altered a protein on the surface of the digestive vacuole.
effectively turning it into an efflux pump.
It became like a microscopic bouncer, just grabbing the chloroquine and throwing it right back out of the club before it could glue the bag shut.
And the fallout from that single evolutionary tweak was devastating.
Chloroquine resistance just ripped across Asia, eventually hitting East Africa by the late 70s.
Within a decade, the cheapest, most widely distributed antimalarial in human history was rendered clinically useless against falciparum in most of sub-Saharan Africa.
The resulting resurgence in malaria mortality through the 80s and 90s, it was a global health disaster.
The world needed a new weapon, and fast.
Which brings us to arguably the most incredible story in our sources.
Yeah.
The rediscovery of a 1,600-year-old secret.
Such a wild story.
So in 1967, North Vietnamese soldiers were dying in droves from this new chloroquine-resistant malaria deep in the jungles.
The crisis was so severe they actually appealed to China for help.
And in response, a highly classified military research initiative was launched. It was known as Project 523.
And pharmacologist Tu Youyou was tasked with leading a team to find a cure.
Keep in mind, this project was initiated during the Cultural Revolution in China.
Right. Conventional scientific infrastructure was in absolute chaos.
But Youyou's team was operating under immense pressure. They systematically screened over 2,000 traditional Chinese remedies.
Just desperately looking for anything that showed antimalarial activity.
And they eventually zeroed in on sweet wormwood or Artemisia annua.
But the lab results were incredibly frustrating.
Yeah, sometimes the extract killed the parasite, and other times it did absolutely nothing.
The breakthrough only happened when Tu Youyou went back to a 4th century text by a Jin dynasty physician named Ge Hong.
Titled The Handbook of Prescriptions for Emergencies, I think.
That's the one. The text explicitly instructed practitioners to soak the wormwood in cold water and drink the juice.
And that detail, that was the key to everything.
Yes. The modern laboratory protocol Tu's team was using relied on hot water extraction.
They were essentially boiling the plant.
And the heat was completely degrading the active compound before they even had a chance to test it.
So realizing this, Tu switched to a low-temperature cold ether extraction in 1971.
And they finally isolated the active compound, artemisinin.
And because Project 523 was so shrouded in secrecy, Tu and her colleagues actually volunteered to test the early extracts on themselves.
Just to prove it was safe for human trials.
The discovery stayed hidden behind the Iron Curtain for years, though Tu Youyou was finally awarded the Nobel Prize in 2015 for it.
Which was incredibly well-deserved.
Definitely. But let's look at the pharmacology here. I'm picturing this artemisinin molecule floating through the bloodstream. What does it actually do to the parasite that makes it so lethal?
It operates on a vastly different principle than chloroquine. The artemisinin molecule contains this highly unusual structural feature known as an endoperoxide bridge.
Okay, an endoperoxide bridge. What is that?
It's essentially 2 oxygen atoms linked together in a very tense, unstable ring.
And on its own, this bridge is entirely inert, right? It travels through the body harmlessly.
Yes, it requires a very specific chemical trigger to activate.
And that trigger is iron.
Exactly, which is perfectly timed because, as we established earlier, the parasite's digestive vacuole is absolutely overflowing with iron.
From all the hemoglobin it's been devouring.
Right. So the moment that endoperoxide bridge collides with the iron inside the parasite, the tense chemical ring violently snaps open.
And this cleavage unleashes a massive storm of highly reactive free radicals.
It's a chemical landmine.
A chemical landmine. That is the perfect way to describe it.
These free radicals act like molecular shrapnel. They indiscriminately alkylate or severely damage the parasite's proteins, lipids, and cellular membranes.
Just a rapid, overwhelming assault that destroys the parasite from the inside out in a matter of hours.
The numbers in the research are staggering. Artemisinin can reduce the parasite biomass in a patient by 10,000-fold within a single 48-hour life cycle.
10,000-fold.
Yeah.
That makes it the fastest-acting antimalarial known to science.
There really is.
But, that makes me want to push back on the history a bit.
Okay, what do you mean?
Well, if we've had a drug that can shred this parasite 10,000-fold in 2 days since the 70s, why hasn't malaria been completely eradicated?
Well, it's the ultimate double-edged sword of pharmacology.
There's always a catch.
Yes, artemisinin is incredibly fast and powerful, but it has an exceptionally short half-life in the human body.
It sweeps through the bloodstream and is eliminated very quickly.
Right. If you administer artemisinin all by itself, a practice known as monotherapy, it acts like a tidal wave, wiping out the vast majority of parasites.
But because it vanishes so fast, it leaves behind a tail.
A small population of stragglers that survive the initial blast.
And those stragglers are suddenly exposed to fading sublethal concentrations of the drug.
Which is the exact recipe for breeding drug resistance.
You're basically putting the surviving parasites through a training montage, teaching them how to withstand the weapon.
The selective pressure it creates is immense. The threat of losing artemisinin the way we lost chloroquine was so severe that in 2006, the World Health Organization had to step in.
Right, they instituted a massive global policy shift.
They strongly mandated against using oral artemisinin monotherapy. The global standard shifted entirely to ACTs.
Artemisinin-based combination therapies.
Exactly. It's the concept of rational polypharmacy.
You take the incredibly fast, short-acting artemisinin, and you basically handcuff it to a slower, long-lasting partner drug.
The artemisinin acts as the sledgehammer up front, and the slower partner drug sticks around in the bloodstream for weeks to mop up the survivors.
That combination is highly effective because the partner drugs utilize entirely different mechanisms of action.
Right. A parasite might survive the free radical storm, but it's immediately hit by a completely different biochemical attack.
Let's talk about those secondary attacks, because the sources mention partner drugs that block the parasite's folate pathway.
Yes, antifolate.
Now, I have to ask, if the parasite is swimming in human blood and humans have plenty of folate in our bodies, why doesn't the parasite just steal our folate the way it steals our hemoglobin?
That is the million-dollar question, and the answer is another critical biological vulnerability.
Oh, really?
Yeah. The parasite is physically incapable of scavenging human folate. It lacks the necessary transport mechanism to absorb it from our bloodstream.
Wow. So it is entirely dependent on manufacturing its own folate from scratch.
Synthesizing it step by step to build its DNA.
So a partner drug like sulfadoxine pyrimethamine, or SP, targets that manufacturing process?
Exactly. It sequentially jams two different enzyme steps in the parasite's assembly line, literally starving it of the materials it needs to replicate.
And then there's another common partner drug mentioned, atovaquone.
Right. Atovaquone attacks the parasite's energy factory. It disrupts the mitochondrial electron transport chain by mimicking a necessary coenzyme,
causing the parasite's energy production to completely collapse.
To survive an ACT, a parasite would need to spontaneously develop multiple, highly complex genetic mutations simultaneously.
Which seems impossible. But, as we saw with chloroquine, the parasite never stops adapting.
Never.
Even with these powerful combinations, the sources outline a terrifying new threat emerging. Around 2008, researchers in the greater Mekong subregion, specifically in Cambodia, they started noticing something alarming.
It was taking longer and longer to clear the parasites from patients treated with artemisinin.
The parasite had evolved a new survival strategy. But crucially, it wasn't a mechanical pump like the chloroquine resistance, right?
No, this was different. Researchers traced this new resistance to mutations in a gene called KELCH13 or K13.
And when parasites with this mutation are exposed to the sudden blast of artemisinin, they don't try to fight the free radicals or pump the drug out.
Instead, they enter a state of profound temporary dormancy.
They literally hibernate.
They shut down their biological processes, hunker down, and just wait for the short-lived artemisinin to leave the bloodstream.
And once the coast is clear a few days later, they wake up and resume growing.
It's a behavioral adaptation rather than a chemical detoxification.
That is so deeply unsettling.
And the chilling reality is that this K13 mutation is no longer confined to Southeast Asia.
It's moving.
It is now being confirmed in parts of Africa, including Rwanda and Uganda.
Given that sub-Saharan Africa carries the vast majority of the global malaria burden, this behavioral resistance threatens to undo decades of public health progress.
It's a very serious situation.
And as if adapting to our best drugs wasn't enough, we still have to confront the final boss of the malaria life cycle. Let's go back to that house analogy we used earlier. We've been talking entirely about the bloodroom. We've thrown sledgehammers and mop-up crews at the bloodstream.
But we have to address the liver room.
Right. This is a vital point. Because while Plasmodium falciparum is the most lethal, there are other species, specifically Plasmodium vivax and Plasmodium ovale.
And they have a unique and devastating capability. They produce dormant liver forms known as hypnozoites.
Hypnozoites? I mean, it sounds like something straight out of science fiction.
It really does. These are parasites that invade your liver cells and just go to sleep.
They can sit there quietly for months, sometimes even years.
They are completely invisible to the host's immune system, and they are entirely untouched by any of the blood stage drugs we've discussed.
So a patient could be treated with an ACT, test completely negative for parasites in their blood, and return to perfect health.
But a year later, those hypnozoites wake up, re-enter the bloodstream, and trigger a massive relapse.
Without the patient ever being bitten by another mosquito.
To achieve what malariologists call a radical cure for these specific species, you have to breach the liver room.
And the arsenal for that is incredibly limited, isn't it?
Very. The sources indicate there is only one specific class of drugs, the 8-aminoquinolanes.
Which includes medications like primaquine and difenaquine.
Right. They are capable of actually penetrating the liver cells and destroying the mitochondria of those dormant hypnozoites.
The precision required to manage this disease is immense. These are highly specialized antiparasitic tools, carefully deployed based on the specific species and stage of the life cycle.
Exactly.
Though, it's worth noting how these highly specialized tools occasionally spill over into the mainstream in unpredictable ways.
Yes.
Looking at the recent history and the sources, we really have to mention the controversies surrounding hydroxychloroquine in 2020.
Right. Hydroxychloroquine being a closely related, slightly less toxic derivative of chloroquine.
Exactly. Early in the COVID-19 pandemic, it was heavily promoted globally as a potential treatment or preventative measure.
It was everywhere in the news.
It was. Now, we're sticking strictly to the trial data in the sources here, just reporting the facts. Massive randomized trials, like the recovery trial in the UK, ultimately found no clinical benefit for COVID-19 patients.
Right, but the initial surge in global attention caused a massive run on the drug.
And the sudden demand created severe, real-world supply chain shortages.
Which had immediate consequences for patients who genuinely depend on hydroxychloroquine for its established medical uses.
Right, not just for malaria prophylaxis, but as a crucial daily medication for managing autoimmune conditions like lupus and rheumatoid arthritis.
It's a stark reminder of how interconnected global pharmacology really is.
An antiparasitic drug designed for a mosquito-borne illness can suddenly become the center of a global supply crisis.
It's incredible.
So taking a step back and looking at this massive historical arc, why does understanding this microscopic warfare matter for you, the listener, today?
Well, the reality is that malaria is still a staggering global burden. It heavily impacts children under 5, especially in sub-Saharan Africa.
The stakes of staying one step ahead in this pharmacological arms race are monumental.
But the encouraging news is that the paradigm is shifting again.
We are entering an era where drugs don't have to carry the burden alone.
They are now deployed alongside robust vector control methods like insecticide-treated bed nets.
And critically, we now have WHO-recommended vaccines such as RTSS and R21.
Which actually train the immune system to intercept the parasite before it even reaches the liver room.
We are finally building a defense that hits the parasite from multiple overlapping angles.
And the unifying lesson across all these centuries of pharmacology remains the same.
Our most durable, effective weapons are the ones that exploit the fundamental biological differences between the human host and the invading pathogen.
Whether we are targeting heme detoxification, folate synthesis, or iron-triggered free radicals, we win by attacking what makes the parasite alien to us.
And resistance emerges the moment those alien biological processes find a workaround.
Always.
Which leaves us with one final, incredibly provocative mystery for you to ponder.
Oh, this is a good one.
As we trace the history of drug resistance today, there is a geographical coincidence that researchers are still trying to unravel.
It's baffling.
Remember how chloroquine resistance first emerged on the border between Thailand and Cambodia in the late 1950s?
Yes.
Well, half a century later, around 2008, that terrifying K13 artemisinin resistance.
It emerged in that exact same border region.
What is it about the specific unregulated drug pressures in that one pocket of the globe that turns it into a recurring incubator for superparasites 50 years apart?
It is a geographical flashpoint that continues to demand the world's closest attention.
It's wild to think about. That microscopic, shape-shifting home invader is always finding a new way to pick the locks. Thank you for joining us on this deep dive into the pharmacology of malaria. Keep questioning the world around you, and we'll see you next time.